morning. Today we begin a new chapter. Here we will talk about structural steel, and in fact this is an area where principle of physical metallurgy has been very effectively utilized to improve the strength of structural steel. And in fact the automotive industries, most of the automobiles, bulk of it is made up of structural steels, and major driving force to cut down to improve the quality of structural steel came from that oil crisis, and main aim was to cut down the weight of vehicles, and this has been possible by improving the strength of structural steels of which these vehicles are made, and so that they are lighter, they are more fuel efficient. And we will see how the principle of physical metallurgy has been used in this particular case to improve its strength very effectively. And in fact, since 1980s very large number of newer grades of structural steels have been used, and these have found application in many other areas as well. And here we will take up, we will first know what is structural steels, then we will talk about a few important points. See, there are steels which we use, they are put in these three category: kiln steel, semi-skilled steel and reaming steel, and what they are and how they are produced. We will also know about a little bit of steel designations. We will talk about strengthening mechanisms. We find out which of this mechanism will be most applicable to improve the quality of structural steel. We will talk about thermomechanical processing by which this is achieved. We will talk about few high strength low alloy steels. This is also known as microalloyed steel. We will talk about the relationship between strength and toughness, and we also know about what is the ultimate, is it possible, what do you mean by ultra high strength steel, and how are they produced, or what goes into improving the strength of steel. And in fact, we talked about this concept, this tetrahedral, where we say that properties of materials depends on composition, that means material, that is the chemical composition, the property depends on this. Similarly, its property also depends on how you process. Say fine grain structure will have higher strength. So, how do you produce fine grain? So, that will affect the properties, and in fact, all these together affect the performance. And last class we talked about the limitations of hardening a steel, because this is totally dependent on the section size, and in many cases if the section size is large, it cannot be hardened, because we have seen by quenching the strength of steel can be increased many folds. So, this obviously will be the most obvious choice for strengthening, but it cannot be applied because it can be attained, that full martensitic structure can be attained only through over a very limited thickness depending on the type of steel that we use. And in fact, this has been used very effectively to find out cases, to utilize this by modifying the composition, and we talked about case hardening. I am projecting this here because I just realized there has been some mistake which I will explain here. So, here when you have a large section, here the core, you want a tough core to be tough. So, one would prefer a low carbon steel, and since it cannot be hardened through and through, the attempt is made to enrich the carbon content of the surface by different carburizing process like pack carburizing or gas carburizing. You increase the carbon content of the case, core remains low carbon content, and when you make this modification, their MS and MF temperature decreases. So, you will find that case will have, this is the MS temperature of case, because case has high carbon content, case has high carbon content. So, here this is the MS temperature, this is MF temperature. So, case has lower MS and MF temperature than the core, and when you cool this, when you quench this job or cool it, try to cool it fast, always core, which is the inner portion, will cool slowly than the surface. But in spite of this, you see the core crosses this MS temperature for core, this is the MS for core, before transformation begins in case, although the case temperature is lower at any instant. So, here you will find that this temperature. So, therefore, what happens at any instant, this before this starts, this is not to scale, it is possible by controlling the cooling rate to allow the transformation to begin first here, case here, and before this starts. So, this line should be, I think, a little this side. So, so trick is the core transforms first when this case is still hot. So, therefore, when the core tries to expand, that case can deform and accommodate the strain, and later on when case transforms last when the core is cold. So, therefore, the core will not allow this to expand. So, therefore, a residual compressive stress will develop on the surface. So, this is the reason why you get because of this difference in MS and MS temperature, by modifying the composition, it is possible to introduce by case hardening a favorable residual stress, that is compressive residual stress at the surface, and by that you improve the performance of this component. And same concept, similar, that this type of principle, basic principles have been used in case of structural steel as well, and we will see how this is done. Now, what is meant by structural steel? It is the cheapest material of construction. Bulk of construction is made of structural steel, and it is cost wise, it is possibly it is only cement concrete structure is possibly the cheapest, and the next cheapest material of construction is structural steel. It accounts for bulk of world steel productions, maybe 1995. Bulk of this production actually is for structural steel, and we call any carbon steel less than 0.25 rather relatively low, and it is virtually plain carbon steel. It has some residual elements which are not intentionally added, which are listed here. Sulfur is undesirable, it gives hot shortness, makes that hot working difficult, and to overcome this some amount of manganese is added to steel. And phosphorus is also detrimental. It has a very high hardening coefficient, it increases strength of ferrite significantly, it improves the solid solution strength, it is a very important solid solution strengthener for ferrite, but it segregates to grain boundary and makes the steel brittle, and it is actually gives cold shortness, responsible for cold shortness. It is brittle at low temperature. And manganese is often used as a to overcome the bad effect of sulfur. It forms manganese sulphide, which has high melting point, and therefore, it does not allow, I mean, it is distributed uniformly in the steel. So, it overcomes the problem associated with hot shortness, and silicon is often used as a deoxidizer, and it also has some beneficial effects as well. but they are not, I mean the amount in the which they are present is very less, like sulfur, phosphorus, you will never have more than, very rare to have more than 0.05 of these, or even better quality these days has even less sulfur and phosphorus. And this microstructure of structural steel is mostly ferritic. It may have some pearlite depending on the carbon content. Many of these grades have as low a carbon content as 0.07. So, virtually it will be made up of mostly ferritic matrix, it will be, and very little amount of pearlite. Because it has low alloy element, it has poor hardenability. So, the martensitic strengthening will not be applicable, strengthening by hardening cannot be done over here. And often you may have some micro alloy additions, is very small amount, even less than say 0.1 or 0.05, and certain elements, if they are added in such small amount and by combining the thermomechanical processing, it is possible to refine the structure to make the grain size very fine and thus improve the strength of steel. Now, let us see what are the factors. I think this was done, but to recapitulate, let us see that okay, a few line about the three major classification of steel. It is based on the way the steel is deoxidized. If you look at the bulk steel production technique, so it is produced from hot metal, which comes from, let us say, blast furnace hot metal, which is actually a cast iron. It has a very high carbon content may be around 4%, it has silicon also, and these impurities, it also has sulfur, phosphorus, and they must be removed to make it steel, because such material, such high carbon material is extremely brittle, they cannot be formed. So, therefore, these impurities are to be removed, and this removal is done by oxidation process. So, in basic oxygen furnace BOF, oxygen is blown from top, and then this oxygen reacts with these impurities, and these impurities are absorbed in slag. And in the process, since the atmospheric atmosphere that is maintained in the furnace is oxidizing atmosphere, steel also picks up oxygen. This oxygen is in dissolved state in liquid iron, and this above. So, and this has to be removed, because as you cool down, you will find unless you remove that steel, if you do not do any special treatment, you often find that this steel, when it solidifies, there is a vigorous reaction taking place. And this is primarily because steel, the solubility of oxygen in molten iron depends also on other alloying element, and particularly carbon. You are trying to remove carbon by oxygen, and this is, and they will be soluble amount of carbon and oxygen that can remain in solution in iron is given by this equilibrium reaction, and the product of concentration of carbon and oxygen and steel is called the solubility product. And this product, it is a function of temperature, it is constant. Therefore, if you plot a graph percentage soluble carbon in iron and soluble oxygen in iron, you will get this kind of a hyperbola, because this equation is that of an hyperbola, and therefore, higher the temperature, higher is the solubility product. So, higher temperature, this temperature is increasing, it can take, say, if it has this much amount of oxygen, it will have this much amount of carbon. But when you cool the steel, when you pour the molten metal in an ingot like this, what will happen as the temperature goes down? So, it becomes, it has higher amount of carbon, and that carbon has to now come down. So, carbon will come down, let us say some line, so it has to come down. If carbon comes down, oxygen also will come down, solubility of oxygen also decreases. So, if it happens, it comes down from here, then what happens to that excess carbon? So, that will react and form CO bubble, and these bubbles try and form, and this is a vigorous reaction, this gas bubble try and form, and what happens, the reaction is extremely vigorous and you have to control it properly. And often normally if molten metal solidifies, there should be contraction and you usually get this kind of a shrinkage. Whereas, in this particular case, if this vigorous reaction takes place, this reaction is called a rimming reaction, rimming action, and that these are the some of the CO bubble which are not able to escape, because if it forms a crust, it will not be able to escape, and in that case you have a steel which is full of the CO bubbles and it compensates this shrinkage cavity, and it has one advantage, you have higher yield, but it has a problem, you have some amount of dissolved oxygen in the steel and oxygen makes the steel brittle. So, rimming steel, although it can be during subsequent rolling, these pores they seal up and all that, but because of some amount of soluble oxygen in the steel, it has a relatively poor ductility and it has higher transition temperature. Other extreme, if you add a deoxidizer, and one of the preferred deoxidizer is aluminum, either which has a very strong affinity for oxygen. In that case, this oxygen will be used up by aluminum or silicon, and depending on what you are adding, the steel, you can stop this rimming reaction completely, and in that case you kill this particular reaction. That means, you kill the steel which is very reactive, you kill it, and therefore, you get a large shrinkage cavity, and when you roll here, of course, the yield is low, because later on you have to crop a certain part of it which cannot be shaped into say flat products or sections. In between also it is possible you have control amount of this deoxidizer, and so that you can control this rimming action, and so that you do not allow this shrinkage to take place. So, some amount of CO bubble is allowed to form, and here by this yield can be increased. Now, a quick look at the effect of carbon content on the properties of steel. I think this was mentioned earlier that with carbon content, yield strength, UTS, hardness, they all decrease, but the ductility, which is represented by reduction in area, decreases with increasing strength or increasing carbon content. Ductility, if expressed in terms of percentage elongation, also decreases, and these are the values of that range of properties that you can get, which are listed here. The Brinell hardness number, the minimum you get particularly when you have virtually no carbon, and say if you have 0.8, you get something like this. UTS, ultimate tensile strength, is of this order MPa, this is megapascals unit, and similarly this also some values are there as a ductility. So, strengthening in this particular these types of grade, it follows rule of mixture. If you increase the amount of perlite, its strength will increase, and by cooling rate it is also possible to control the fineness of perlite. If you increase the cooling rate, perlite, if it is finer, then also the strength will increase. Now, few points about steel specifications. See, obviously, most of the specification are based on compositions. Now, different countries follow different Indian standard specifications, which is listed here. Say suppose carbon steel, if it is a plain carbon, one way of representing is C07. Here this number represents percentage carbon. So, percentage carbon means here you divide by 100. So, 0.07% carbon, this steel C07 represent this. C15 means carbon content is 0.15. Now, sometime you have certain other alloy element, there you do not write C, you write that main alloying element which is present. So, you say that 15 Mn1, and when first two number, this represents carbon content. So, that is 0.15 is the carbon, and the second one gives the manganese content, 1% manganese. Sometimes these elements, you have more elements, like there are certain grades we mentioned that where normally sulfur is undesirable, but there are certain grades where you add sulfur. This is particularly where you need very good machinability. There you need a little bit of inclusions made of manganese sulphide, which improves the machinability of steel. So, this is one such steel. Here 0.25 is the carbon content, manganese is 1, and sulphur is 0.14. And in fact, sometime you use underline to show that this is 0.14, it is not 1.4 or 14, it is which is unexpected, unheard of. So, that means it is underlined, means if any number is underlined, say if it is 5 underline, that means it is mean 0.05, or 15 underline is 0.15. Now, many of these have been derived at systems, from the system followed by American Iron Steel Institute or Society of Automotive Industries Enterprises and automotive engineering. So, these are this AISI specification is written like this. You use 4 digit, the first 2 digit which can be represents the type of steel, and the last 2 digit this represents carbon content, like XX25. This 25 means this carbon content is 0.25. It's there is a mistake here. This should be 0.25 is the carbon content, and this XX, if it is 10 means it is plain carbon steel. This first 2 digit, if it is 10 means plain carbon steel. First 2 digit, if it is 11, this is resulfurized steel. 13 means manganese steel. 40 means moly steel. 41, this is the convention, there is no basis, but sometime if you follow this convention, it is possible to guess what is the composition and what are the major alloying elements. 41 means you have chromium molybdenum. These are alloy content, amount may not be much larger, maybe 1% or 2% around that. So, 43 means nickel, if you have first 2 digit is 43 nickel chrome moly, first 2 digit 51, in that case this means it says 0.8 chromium steel. 52, then it is a chromium steel, this is a bearing steel, 1.45 chromium. 61 means chrome vanadium steel, 92 silicon manganese steel. So, one example which is given here, 1025, this is actually the carbon content is there is a mistake here, 0.25 carbon steel. This is a ball bearing steel, here 5210. So, this has 1.45 chromium, and these last 3 digit represents carbon content, and carbon is 1%. Now, British specifications, that old specification there is no basis as such, like these are some certain number engineering steels EN 24, which is equivalent to SAE 4340, and this is the composition of that steel. And the new BS spec, they use digits like this, first 3 digit they signify composition alloy element, last 2 digit gives that last two digits gives the carbon contained, and it also uses certain letters A, M, H, which means that specification is by analysis, by mechanical property, or whether it is a hardenable grade. And in fact, this specification varies from country to country, and attempts have been made to use unified numbering system. And here UNS system, and here the G, they use a letter grade to represent G for carbon steel, S for stainless steel, T for tool steel, and you can see this is simply a plain carbon steel, and you find out this will be a 0.2% carbon steel. Now, let us see, so we have talked about some steel specification. We also learned that structural steels, what is structural steel, is basically plain carbon steel. And now, let us see what type of strengthening mechanism will be applicable here, because here since the section size depending, sometime it can be very large, and sometime and it has very low carbon content, low alloy element, therefore, it has little hardenability. So, therefore, the strengthening mechanism which are normally applicable in steel, which are listed, but all may not be applicable. We will see which will be most preferable. So, one is a solid solution strengthening, we learned some about this earlier, then strain hardening or work hardening, grain refinement, precipitation hardening. These are the common strengthening mechanisms which are used to improve the strength of steel. And if we or any metals, any metal and alloy, these are the basic strengthening mechanism. Just to give an idea, say what is the strength of steel? Iron can be made in the form of whiskers. These are very fine filaments which are grown from vapor phase, and these are so fine, that means the distance, normally we have seen the dislocations, they have a stress field, two dislocations cannot stay very close by. So, if it is possible to find out or make a material where the two dislocation, it is impossible to accommodate a dislocation. If the dimension is very small, it is quite likely that this material will be defect free. And these whiskers are very thin filamentary crystal, and these are virtually dislocation free, and its tensile strength is of the order of 10 GPa. By cold drawing 1% carbon steel, we will see how it is undergoes a very special deformation process, by which you can achieve this in actual practice. Benitic steel, having the carbon strength will obviously depend on amount of carbon that is there. If it is 0.8, you can get this level of 0.15 gigapascal strength, whereas low alloy martensitic steel, you can get strength of this order. But very often the structural steel that we use, they are not martensitic, and let us see how we can strengthen them. Now, in structural steels, there is a limitation in strengthening mechanism. What are they? Now, there are common forms of structural steel, say very common, say it could be I beam, it could be L sections, it could be plates, it could be strips, or it could be cold rolled sheets, it could be pipes, tubes, bar, wire rods, wires, wire ropes. So, there are so many, and when these structural steels are made, they are often required to have not only strength and toughness, but certain other additional properties. This depends on what is the downstream application of these. Say suppose you want to form for automotive body, which is made up of steel sheet, thin steel sheet. So, in that case, property that we look for is formability, and often just formability is also not enough. Sometimes you have to join or give a proper shape it is should be amenable to certain fabrication process, like welding is one such fabrication process. You have to look at the weldability. Sometimes certain application machinability is important, and many application you will also look for the material should be able to withstand corrosion, it should be corrosion resistance, and many of these we will see can be met by limiting percentage carbon in steel. But the problem comes up, if you decrease percentage carbon in steel, its strength will go down, and how do we make it up? That is, and let us see how this is possible. Now, a quick look at the strengthening, solid solution strengthening. If you add a solute atom, this atom like here, you add, it will have a different dimension. So, there will be some elastic distortion, it will have a stress field, and we know that deformation takes place through movement of dislocation. Suppose this dislocation is moving in this direction, this is a stress field. So, this is not free to move. So, this dislocations movements are hindered by the stress field of these solute atoms, and overall effect will depend on how closely they are spaced. So, if and therefore, say proper, so it is, so more the number of atoms, more will be the strengthening, and people have, it has been possible to work this out, and we will see quickly here on this sheet. Now, it is possible to find out that how much force is exerted by the solute atom on the dislocation, and this force will depend on, you know, if you have more number of atoms. So, what is more important, what is the force which is per unit length of the dislocation exerted by the solute atom. If d is the spacing between two solute atoms, then you can say this is the force per unit length, and to move the dislocation you apply a shear stress tau. In that case, force on the dislocation will be tau b, and the both have to be equated. If you equate the both, it is possible to find out a relationship between that it is also possible to find out, if you know the atom fraction of solute present, it is possible to show that the distance between two atoms will be roughly equal to 1 over root over atom fraction of that solute element, atom fraction of the solute element, and therefore, and if you make just a substitute over here, then you will find that increment in tau, the shear strength, will be proportional to square root of the solute contained, and this is the case where solute atom is a substitutional solute atom, and same thing can be extended to cases in the interstitial atom also. But interstitial atom, we know that in face centered cubic, in FCC, that means in austenite, carbon occupies, let us say, octahedral site, and these sites are symmetrical. So, in FCC, that whenever you have a carbon atom, distortion that it produces is uniform in all directions, whereas in BCC lattice, you know, even if the carbon atom, whether it is tetrahedral or octahedral, and more likely chance, I mean, people have seen by experiments that carbons are preferred sites at octahedral, and these octahedral sites in BCC, they are not symmetric. In one direction it is large and another direction it is short, the gap, interstitial gap is shorter. So, when carbon atom goes into the interstices, it produces expansion in one axis, and that axis is C, and this introduces a tetragonal distortion in the lattice, and this distortion is quite large, and that is a more important factor for strengthening, and therefore, interstitial atoms produce as I summarized here, in symmetric distortion in FCC, but asymmetric in BCC, and therefore, in asymmetric distortions are more effective in blocking dislocation movement, because uniform stress can block only edge dislocation movement, whereas asymmetric distortion will have shear stress, and therefore, it can block the screw dislocation motion as well. So, therefore, they are much more effective barrier to dislocation motion, and they have a good high amount of strengthening effect, and this also will be nevertheless proportional to the number of atoms that you have. It is also proportional to square root of atom fraction. So, this is applicable for interstitial, and this is the relationship for substitutional atom. Now, strain hardening we have seen, that is, this is a typical deformation behavior of a single crystal. We talked about 3 stages: period of easy glide, where there is a little dislocation interactions, whereas in the stage 2 it is a period of linear hardening, where dislocation interaction takes place, Cottrell Lomer locks are formed, the jogs are also formed on the dislocation, and this makes the movement of dislocation difficult. So, therefore, there is high amount of strain hardening, and then when the stress increases significantly, here again another mode of deformation which is responsible and leads to little bit of softening, that is cross slip. So, this is the third stage, and in general this is the behavior in a single crystal, but polycrystal you have large number of grains. So, you do not see these 3 distinct stages. What you see, this is a typical stress versus strain plot in case of a polycrystalline material, and here the total strength of the material will be determined by the dislocation density. Higher the dislocation density means you have more dislocations in the slip plane, and dislocations, because of the dislocation interaction, it forms tangles of dislocations, and what is more important is if the dislocation density is increased, the distance between 2 dislocation also will decrease. The dislocation between dislocation node will decrease, and it is possible to show that the strength, as it is shown here, that the strengthening is proportional to square root of dislocation density. Here G is a shear modulus, B is Burgess vector. So, this dislocation density. So, the main strain hardening mechanism is primarily increase in dislocation density, and its dislocation networks becomes very fine, dislocation distance becomes smaller, and the strength increases. Another important strengthening mechanism is grain refinement. When a dislocation source acts on these are the 2 grains, let us assume. If a dislocation source is operating, it will generate dislocation, and when it moves through the slip plane, it causes it deforms the grain. And in doing so, that is possible, it can come across a barrier, and here this dislocation it stops, and a pile up develops, and this also leads to strain hardening, and depending on the size of the grain, it has a limited capacity. It can accommodate only a limited number of dislocation, and this grain boundary also has a finite strength, and if this number of dislocation increases, stress on the grain boundary, local stress gets intensified, and it can move into the dislocation and this area grain boundary, or it can move from here to next boundary, it is possible. And so, therefore, the grain size is an important factor. It determines how many dislocations this can accommodate, and it is possible, if you recollect your earlier lecture, it has been shown that strength of the crystal polycrystalline material is inversely proportional to square root of the grain size. D is the average grain size. And in fact, this is the plot which a diagrammatic representation. If you plot yield strength against 1 over root D, you will get a linear line, and in fact, from this you can find out sigma 0 and k. And we also talked about precipitation strengthening at length, and in fact, there are two mechanisms which are important. One is a particle looping, another is a particle cutting, and we said that this is the limiting strength, the critical resolve shear stress or critical strength of the material, and here this is the looping stress, and this is directly determined by the it will be by particle distance, and for a given volume fraction of precipitate it can be related to the particle size also. And this has this kind of a relationship, and in the meantime you also have the particles. See, initially you do not have any precipitate. As the precipitate grows, the volume fraction of precipitate increases, and the precipitate also grows in size, R also increases, and the stress required to cut a fine precipitate is given by this volume fraction of precipitate raised to the power half and radius of the precipitate raised to the power half. So, this plot looks like this. So, this is the optimum strength that you expect. After that, if the precipitate coercion, then the strength drops. So, to get ideal strength, maximum strength, what you need is you need high degree of supersaturation. So, you need a supersaturated solid solution, and then when you age, the precipitate that forms must be coherent precipitate, and the coherent precipitate is always associated with some lattice strain. We talked about this lattice strain. If there is too much of lattice strain, the precipitate is trying to form. So, this will oppose the driving force. So, therefore, too much of lattice strain is also harmful. So, you may have some amount of lattice strain, coherency strain it can accommodate. So, basically some low strain energy, not too much, and then coherent precipitate and high supersaturation. By controlling this, you can control the extent of precipitation strengthening. Now, by most of these strengthening mechanisms, if you try to increase the strength of crystal, what happens, what effect does it have on the ductility? And if you recollect our that initial plots of the stress strain plot, normally the brittle material are those which break even before plastic deformation occurs. So, a brittle material, say a stress strain plot, will be virtually linear, and here it breaks. So, in fact, martensites, if you have a fully hardened, say wire, steel wire, which have been hardened to martensite, fully hardened, if you try to find out its stress strain diagram, you will find it is before it deforms, it breaks. But the same steel wire, if you anneal, you make it ductile, in that case you will find it exhibit this kind of a stress strain behavior. So, before it fails, it passes through a necking region, and you have a very large percentage elongation and reduction in area. So, in fact, it has been seen that if you try and improve the strength of the material, whether it is by cold working. So, if you take a wire and try and bend it repeatedly, each time you bend, you are deforming, causing some deformation in the material, and its strength increases, and in the process it reaches its limiting strength, and later on you find it breaks. You try to deform it, it breaks. So, that means if you increase the hardness or strength of the material, yield strength or tensile strength of the material, then its elongation, ductility decreases. And there is also another term we talked about, ductile to brittle transition temperature, which is quite important for structural steel. Many of the structures which are made of say thick plates, say particularly ships which go into regions in the sea where sea is cold, and these plates, one of the main fabrication technique is welding, and when you weld and thick plates, you have to see by welding you do not deteriorate the properties in the welded region, and you do not increase the strength and adversely affect the toughness of the material. And one mechanism, so one problem that comes up in any of these fabrication process or alloy element is when you improve the strength, its ductile to brittle transition temperature increases. So, certain steel which is normally it is quite ductile at room temperature, but if you test it at a low temperature you will find it is brittle. So, temperature at which this transition takes place, brittle to ductile, is called ductile to brittle transition temperature, and a high ductile to brittle transition temperature means the material is susceptible to brittle failure at low temperature. So, normally if your strength increases means ductile to brittle transition temperature also increases. Now, most of the strengthening mechanisms which increases they adversely affect ductility, toughness and the ductile to brittle transition temperature. There is one mechanism which is grain refinement. This is the only mechanism that improves yield strength, at the same time does not adversely affect ductility or toughness, and in fact, some cases it is reported to have lowered the ductile to brittle transition temperature. Normally, when a fracture takes place, we will see that whenever fracture takes place, there are certain crack paths which are favorable. Now, usually at a room temperature, we find these grain boundaries are stronger. Normally, at room temperature, grain boundary strength of grain boundary is greater than strength of grain. So, if a fracture takes place at room temperature, it is more likely that the fracture takes place through this. Now, in certain cases it is possible that because of certain if the grain boundary is say in certain cases some solute element they segregate to the grain boundary, and that makes the grain boundary brittle. In that case what happens, because of the segregation cold shortness, these grain boundaries. So, these are grain boundary. So, if these grain boundary some segregation has taken place and this is brittle. So, one amount of segregation we talked about is a thin network of cementite, brittle cementite network, or some monolayer kind of precipitate or monolayer, say suppose phosphorus segregates here. It makes the steel brittle because this provides say low easy fracture path. So, crack can propagate like this, intergranular fracture. So, in that case you have a material becomes brittle, it has intergranular fracture. Now, what happens if you make these grain boundaries finer, you reduce the chance of this segregation because you have more amount of grain boundary. So, chance of this kind of a brittle network forming is reduced. So, this is one reason which makes fine grain steel more resistant to crack growth. So, this is a mechanism which helps improve the strength without sacrificing ductility or toughness. And now, a quick look about how do you control the grain size in steel. So, one method is by cold working and annealing. You can, by this process we did talk about it, by cold work and annealing it is possible to get both very coarse grain structure as well as very fine grain structure. And how do you do? This is a typical annealing curve. When you anneal, if you have a cold work material, it has a very high hardness, and let us consider it is a low carbon steel, it is a very low carbon content, it is mostly ferritic with the, and what happens And the recovery stage, there may be little increase in hardness, this is a strain aging. Sometimes the solute atom, particularly this interstitial carbon and nitrogen, they can precipitate and block the grain boundaries, and this can increase a little bit of strength, but it helps in removing the residual stresses, micro stresses through rearrangement of dislocations. And after certain temperature, there is a rapid drop in strength. So, here what happens, the new grains form, new recrystallized grains are formed, and these grains are strain free, and say like which is shown over here. So, these are the grain structure before working, and when you cold work, these grains get elongated and you have large grain boundary area. And when you heat here during annealing, what happens, this it has a high elastic stored energy, and it will try to come to its position of lower energy. So, there is a driving force existing, but fresh grain cannot nucleate, because to nucleate new grain, new area is to be created. So, this is the main one has to overcome the barrier, that surface energy barrier has to be overcome, and this grain boundaries provides such heterogeneous locations where it can easily overcome. So, these are the nucleation sites, and when these grains grow, and finally, all of these they are replaced by these types of fine grains. Now, cold working, in fact, it increases surface area to volume ratio. So, you provides more sites for nucleation of strain free grain. So, it means it is more nucleation site, and higher the cold work, finer will be the grain. And by controlling the amount of cold work, it is possible to control the grain size, and usually the annealing temperature for cold working, after cold working of low carbon steel, is in this regime. You do not go to the austenitic region. So, definitely the perlite, if at all is there, the perlite area, if it gets deformed, it will remain like this. They do not undergo any recrystallization, but ferritic region will undergo recrystallization, and you will recall that these are the critical nucleus size. So, this grain size will be determined by this critical nucleus, which is inversely proportional to the cold work. So, higher the cold work, finer will be the grain, and also higher the cold work, much lower is the activation hill which is to be overcome. So, the nucleation rate will be faster. Faster nucleation rate means finer grain. Now, hot working is a process where recrystallization and plastic deformation virtually takes place simultaneously. It is possible to calculate the time it takes for recrystallization to take place, because the recrystallization process will be determined by the movement of iron atoms within the lattice. So, self diffusion of iron. So, it is possible that we know the self diffusion coefficient is given by the exponential minus q by RT, where q is the activation energy. So, if you know the activation energy for self diffusion, it is possible to calculate the time for recovery and recrystallization. And often, say if you do it for 800 degree centigrade, you will find that time may be of the order of few seconds. So, that means by the time the job cools, if you are working at this temperature, the time it takes for the job to cool to room temperature is enough for recrystallization to take place. So, when the job cools, you will find it is soft. So, hot working is actually, you can see that there is instant recrystallization on plastic deformation, which is pictorially shown here. So, if you have this, these are the initial, that coarse grain structure, and during rolling these grains get elongated, and these are the nucleation sites, and after this also temperature is high, the fresh grains are forming. And to get fine grain, what you can do, you have to increase the decrease the diffusivity. And how can you do it? That means you finish that rolling to to a temperature just above the recrystallization temperature. So, that atom movement if you can restrict, that means your finished rolling is done closer to the recrystallization temperature and do not allow enough time for grain to grow. So, the key to fine grain structure, develop fine grain structure, if you are doing by hot working, you give all that reduction, major reduction, bulk of it maybe at a high temperature where you need low load rolling load, but give a finished rolling temperature should be low, and this finished rolling temperature also the reduction should be little high. So, that your critical nucleus size is less and you do not allow and the finished rolling temperature is close to its recrystallization temperature. So, as it comes out of the rolling mill, it does not get enough time for the recrystallized grains to grow. And also the austenite grain size also determines that finer structure. Initial grain size if it is coarse, and if you deform it, final structure is likely to be coarse. If initial grain size, austenite grain size is finer, you will deforming it further, you make it more fine, and the chance of getting a fine grain is higher. And this also we know that austenite grain size does affect this CCT diagram, and which is pictorially shown here. So, in this case if the grain size is fine, the transformation starts at a higher temperature. If grain size is coarse, transformation will take place a little lower temperature. So, by playing with this, it is possible to control the final structure of steel. And to sum up whatever we have covered today, we talked about structural steel, talked about steel specification, where we again emphasize the effect of carbon content on strength and ductility. We talked about strengthening mechanisms which have been applied or which can be applied. We talked about strength and relationship between strength and toughness, and we have seen how by controlling grain size it is possible to increase both strength and toughness. And we also talked about how to control grain size by controlling degree of working and the recrystallization temperature. And we will see in the next class a little more about it. Thank you very much.